Hello, my name is Gabe Fierro. This is my dissertation talk recording. Uh, During the actual dissertation recording on April 30th, I forgot to record the first 10 or so minutes. So I'm going to re-record that portion now and then cut back to the full presentation as it happened on the scheduled date. So the title of my thesis is Self-Adapting Software for Cyber-Physical Systems. My name is Gabe Fierro, and here we go. So our world is becoming increasingly digitized. And what I mean by digitized is there is more and more data being produced about the world from increasing diversity of places, different sources, and it's being applied to increasing numbers of domains. And so this not just the IoT devices that we have inside our homes and our buildings. There's also efforts by national governments to digitize representations of all different facets of infrastructure in an entire nation. The city of Singapore is tracking cars and parking availability live across the entire city. Chicago is deploying air quality sensors and water quality sensors across the broader metropolitan area. New kinds of sensors are being deployed in our electric grids and smart grids to measure power quality and look for issues. And even open government data efforts, such as this one from the Alameda County, give us increasing visibility into not just where municipal efforts are taking place, but how land is actually being used. And so there's all this data that's becoming available for analysis and to be leveraged by people, but that data is increasingly hard to use. And the common phrase that's used here is data rich, but information poor, in that we're able to track all of this phenomena in some database, but we're lacking the information that allows us to make use of that data, to understand what that data is telling us. And this is actually a significant bottleneck. A recent survey of data scientists by the website Kaggle found that 40% of that time is spent cleaning and understanding and parsing that data. The amount of time goes up when you're considering the metadata. What is this data about? Where is this data coming from? And the result is that looking at a new data set or considering a data set is this manual, time-consuming task that the conclusions you draw from it can be error-prone, and it just generally takes a lot of time. And when we look at data that's in the built environment and these critical infrastructure domains, that barrier to understanding data impedes the adoption of sustainable practices such as energy efficiency. In 2004, the lack of interoperability between data that was being collected was estimated at almost $16 billion a year. 12 years later, we have better protocols for maybe communicating that data, but capturing the context and the semantics of what the data is telling us about the domain, we're still lacking. And even more recently, even though 70% of commercial buildings have digital control systems deployed inside them that allow those buildings to be controlled and operated in an automated fashion, only 4% of those actually have any sort of automated analytics actually examining whether or not that building is operating effectively. And so why is this? Why is this data so hard to contextualize and understand? And part of the reason is when you go to your building, to use this as a representative example, when you go to your building, you're faced with a interface that looks something like this. This is a screen from the building management system, sort of the OS for a building. And this it depicts the flow of air in one of these pieces of equipment that's in that building. But I want to draw attention to this label here. This is a label for a point, which is a source of data. This might be a sensor. This might be a little register on a controller that's telling how a piece of equipment is behaving. But it's got that label there that basically tries to tell us what exactly this data means. And there are tens or hundreds of thousands of these in a typical system. And this label is supposed to capture everything about what that data is about and where it is in the system and how the system is behaving. And so this poses some challenges. So if we take this example point name from the computer science building on the Berkeley campus, it looks like this sort of string of characters, and we can, if we're an expert, we can parse out what each of these components mean. The name of the building is SODA, but only the first three letters, SOD, actually map to the site name. A means there's some piece of equipment. It's got some identifier that's connected to some region of the building down the line that has some identifier. This actually implies that there's other equipment in between these two places that's not actually captured anywhere in the point name. There's some random delimiter here just to make sure that the entire label is a fixed length. And then finally, at the end, we actually get what the data is about, which is this is a control target for some temperature process, which also implies that there's some controller somewhere that's actually trying to make the temperature meet that control target. And so, there's a lot of complexity here. There's a lot of implied information that I'm able to parse through just because I'm familiar with this building. And that's basically the state of the art. Broadly, site-specific conventions. Sometimes you don't even have these labels, but essentially, there's no consistent, no consistent or standard way of writing down how these systems are put together or what these data sources mean. And so if you go to another building, you go to a bunch of different buildings, they're all going to have a completely different way of writing down that information, of capturing, what these data sources are called, where they are, what the kind of system they're deployed in is, and so on. And so when every single cyber-physical system, every single, system that we're looking at has its own labeling scheme, trying to analyze these and parse out what the different parts mean just cannot scale. This is just absolutely infeasible to do at the scale of, hundreds of millions of buildings around the world. And so where we are is this regime where each time we want to do some piece of analysis, each time we want to look at some data, train a model, identify some faults, we have to essentially re-implement our code, re-implement our analysis for every single building or every single site where we want to deploy it, because they all have different labels, they all have different, different types of equipment and systems inside. And what I'm going to propose in this thesis is, rather than this sort of exhaustive re-implementation across the entire domain, is a new regime where that implementation can happen once. We can write that code once, and it has access to information about these systems that allows it to bootstrap itself or self-customize its operation to each of these individual sites without a human having to be involved at all. And so this paradigm, which I'm calling self-adapting software, describes software that's able to discover enough about its deployment or its environment in order to configure itself automatically. So that's the goal. And this brings us to the thesis statement, which is that the significant barriers to the adoption of data-driven sustainable practices can in fact be overcome. And how we're going to overcome that is through the adoption of standardized semantic metadata. These are descriptions of the data sources and the systems that capture the meaning and the function of what they're going to do. We need data systems that facilitate the management and maintenance of that metadata. We need to be able to create these descriptions and leverage them in our applications. And then lastly, we need new programming paradigms that allow that metadata, that semantic descriptions of these systems, to be exploited by software in order to reduce the configuration costs. And along the way, make it just dramatically easier to work with any sort of cyber-physical data. So this brings me to the talk outline. So I've just given you the introduction. I'm going to go over some brief background on cyber-physical systems, just so you're aware of some of the complexity that's there. And then I'll delve into each of the core components of the solution. First, we'll focus on the form of that effective semantic metadata. Next, I'll talk about continuous metadata integration, or how that metadata can be bootstrapped from existing representations and maintained over time. Then I'll talk about how self-adapting software can actually be enacted, and what a platform might look like for supporting self-adapting software. And then lastly, I'll dig into an efficient query processor, which enables the use of the semantic metadata at a large scale. Then I'll talk about the application to real-world settings and talk about some of the field studies I've had the opportunity to participate in over my PhD, and then touch on some future work. Okay, so the built environment, I've used this term a few times, and what it means is essentially anything that is constructed by humans that is part of our society. So cities and buildings, electric grids, water treatment plants, transportation systems, and so on. And what's characteristic of these is that they are complex. They are undertaking, specific physical processes to manage large amounts of resources that are critical for cities and buildings and humans to operate. They are heterogeneous essentially every one of these systems is a completely unique assembly of components that's been growing organically over time. No two buildings are alike, no two water treatment systems are alike. And they're all constantly changing. Things are being remodeled, they're being redone, new types of equipment are being invented, there's new products on the market, sensors are being deployed in these systems. So they are very protean in nature, they're changing all the time. And these are all challenges that we're going to have to deal with. And to give you a little sense of what's going on inside a commercial building, here's a sort of high-level depiction. We've got an air handling unit. This is a big piece of equipment. This is all in blue. It's outlined in red. This usually sits on your roof, and what it's going to do is it pulls air from the outside. It's going to filter out particles. It's going to heat or cool that air by these coils introduced into the airstream that have hot or cold water running through them. It has a supply fan that's going to blow the air through ducts, where they get to another piece of equipment called a VAV box, or a variable air volume box, that also has a little damper in it that's going to control airflow. It might have another coil that heats the air up or cools the air down. Finally, that air gets delivered into the spaces where we live, work, and sleep, and eat. Then the air gets shuttled back out into the air handling unit. It gets mixed with either it gets exhausted to the outside, it gets remixed from other air returning from the building, and this all cycles through. And all throughout this system, there are sensors that are measuring the humidity and the temperature and the flow of air, the temperature and flow of water going through these systems. There are actuators that control the speeds of fans and the positions of valves and dampers, and all of the different pieces of equipment that come together to make the system work. And this is, pretty, broadly speaking, this is fairly standard. These types of buildings consume about 40% of the energy in the United States. But each of these systems is, they're all slightly different. And, despite all the complexity here that I just talked about, I'm leaving out also a whole bunch. I'm leaving out not just a bunch of detail into how those types of equipment actually work, but I'm also leaving out lighting, electrical metering, plumbing, chilled and hot water systems, fire systems, security and access control, any sort of server room, HVAC stuff that's going on. And again, all of that is custom to each of these buildings. And it's not just buildings as well. Smart grids and wastewater treatment plants and a number of other sectors. There's been a growing call for these systems to be modernized and be digitized and better monitored, not just for more efficient operation, not just for more robust operation, but also, trying to understand these complex operational challenges arising from, PG&E electricity shutoffs in California for fire safety, or understanding the impact of a shut-off gas line on downstream industry, or understanding what a flood or bad weather might do to a water treatment plant. And through all these sort of resiliency scenarios and these issues that come up, we have increasing numbers of sensors, increasing volumes of data measurements being produced and gathered about these systems. And so there's more and more data that's being produced. It's being used in increasingly diverse ways. And this is leading to an increase in adoption of data-driven practices, and essentially what is driving the need for things like self-adapting software. Okay, so we have these cyber-physical systems. They're complex. There's lots of data. How do we actually represent these? What do these are supposed to look like? And the way we're going to do this is with a metadata graph. So the metadata, or the data about the data that we're going to analyze, needs to fulfill a certain set of properties, and needs to represent certain things. It should represent the entities, the actual stuff, the data sources, the things that are there in the system. We want to be able to describe these entities with concepts. So we don't just know the type and their definition, but their purpose and their behavior, why they're there and how they're functioning. And lastly, relationships. How do these entities relate to one another? How are they connected? How do they interoperate in order for the system to behave? And you might think that, given how intuitive or how basic those concepts sound, surely someone must have done this before. But the answer is largely no. There are plenty of digital representations of these kinds of systems, and I'll show a little bit of those later on in the talk. But these do not actually address the needs of data-driven applications. They don't actually describe the data sources and what they're doing. So this is a problem that needed to be solved. So the goals of this metadata system that we're going to design, it should be complete in the sense that it should name all the things that we need to be able to name. It should be expressive. It should be able to talk about, these diverse systems, the different ways in which these complex pieces of equipment should, interact with one another. It should be consistent. The way, two people describing the same kind of system should describe it in fairly similar ways. That should rely less on personal opinion and more on the facts of what's actually there. And then lastly, it should be extensible. We should be able to add new concepts. We should be able to grow these models to account for new kinds of equipment, new technologies, changes to the environment, and so on. And so these design principles have been realized in an artifact called BRIC, or BRIC Schema. And BRIC is a collaborative effort from a collection of researchers at the institutions listed there. And something that I've been in charge of maintaining for the past 5 or so years. And what BRIC is, it's a graph-based metadata ontology. So it's a formal representation of knowledge for smart buildings. And what it's going to do is describe not just the physical things that are there, but the logical and virtual things that all make that system what it is. It's going to describe their behavior and purpose using a class hierarchy. It's going to describe the necessary relationships between those entities. And later in the talk, I'll show how the context that we're going to build up in this BRIC system is going to describe the data we're getting out of these systems. Okay, so what makes BRIC BRIC? BRIC contains a core set of classes that tell us what entities are and how they behave. There's 3 main categories of classes. The first one are the data sources or points. And this encapsulates not just sensors, which are transducers giving us data about the environment, but also set points, which are control targets, commands, which are sort of specific actuations given to devices. And you can see that this is sort of organized with more general concepts towards the top of the hierarchy and more specific concepts towards the bottom. BRIC also represents equipment, which are the physical things that are in the building that are actually, taking action. And BRIC describes a collection of these concepts across HVAC domains, lighting, electrical subsystems, fire safety, and so on. And BRIC also describes locations, building sites, floors, and rooms, different kinds of rooms, but also logical locations like HVAC zones and lighting zones, which are useful for understanding how buildings operate. And BRIC also defines a set of relationships that tell us how different kinds of things interact with one another. And the secret sauce here is the fact that you actually don't need that many relationships to understand how a system is operating. So the is point of relationship tells how a data source relates to the things around it. What is that data about? The has part relationship denotes composition. Locations are made up of other locations. Equipment are made up of other equipment. Feeds is sequence, so how are things connected? So equipment can be connected in some sequence for feeding air or water or light or electricity into some endpoint. And then lastly, location, where are things actually physically located? And with this small number of relationships and small number of core concepts, BRIC's actually able to describe a large array of buildings. To give you an example of what that might look like for a simple building, we'll start with I'll give you an illustration of the BRIC model. So where the ontology is the formal description of what these things actually, how these things are defined and how they work. The model is the instance of a particular building that we can write down in this digital form. So we'll start with the entities or the things that are there. Those are the blue nodes. To describe what each of those are and how they behave, we associate with them one of the classes from the BRIC ontology definition. So you can see we've got the air handling unit equipment I talked about before. You've got points down at the bottom that, measuring airflow and air temperature. And then lastly, relationships show how these different instances of these things are connected together. And so you can see a zone consisting of rooms. You can see a piece of equipment that has another piece of equipment, a damper inside it. You can see the data associated with these. And what I'm going to build up to over the course of the talk is how BRIC is going to enable self-adapting applications. And it's essentially serving this role in that stack here of the metadata. It's going to describe the data that those applications are going to use. And to make this work, it's easy enough, or we can imagine how we might adapt that software. If it's just one building or two buildings, you don't actually need to invest in anything like this. But when n is 100 million or a couple 100 million, you really do need a formal representation of that knowledge that can be used by tools to drive a lot of this process automatically. So to give you a sense of what's sort of under the covers here, Brick is built on the RDF data model. This is a directed labeled graph. It's a way of writing these graphs down. Here's a simple, relatively speaking, simple RDF model that describes a thermostat and a sensor, temperature sensor that's associated with it. You can see how we might write that down. Sparkle, or SparkQL, is a query language for those graphs that allows, this is what the applications are going to use to find this data later on. And so it's a simple sort of graph pattern matching query language that can identify sort of subgraphs and pull out the necessary information. And so this query here on the right is a query that retrieves the names of the thermostat and the name of the temperature sensor. And you can see how those sort of patterns line up against the graph. And lastly, Brick is built on OWL. And OWL, which stands for Web Ontology Language. Yes, the letters don't line up. This is a formal language for encoding semantics, so representing meaning in a computational way. And there's a lot to unpack there, but sort of in a simple example, what these classes are is these classes are essentially sets. So if you have an entity that's an instance of a class, it means it's a member of a set. And so subclasses, or the subclass relationships here, essentially to say which set you're in. And if you are a member of a specific class, like an air temperature sensor, you're also a member of all the sets that enclose you. So one way that that meaning can be captured in a structured way. And so here's the RDF for what a supply air temperature sensor looks like in Brick, and you don't have to parse through all that. But essentially, Brick, using these formal mechanisms, allows users or the model to answer questions like, what substance does the sensor measure? What property of that substance is measured? What kinds of units are valid? Are there similar kinds of sensors in the building? Is the way that we wrote this down correct or valid, or make sort of even physical sense? And all these kinds of questions and these properties are enabled through that formal definition. And what was sort of new about Brick was the fact that it's essentially a new kind of ontology. The semantic web stuff and the RDF and Sparkle and OWL and the rest of that has been around for a while, but it's largely been relegated to the sort of esoteric academic domain. Cory Doctorow, the blogger, famously called it SemWeb hipsters and their meta crap. So this is the sort of, the world that we were walking into. But by modeling the requirements of applications rather than trying to model some abstract philosophy, we actually found that these complex systems actually look a lot simpler from the perspective of an application. And so Brick is designed for usability. That ontology and those formal definitions are there to sort of make sense of, allow software to make sense of what's there, but users don't have to necessarily worry about all of that. You get a lot of stuff for free. And so Brick's actually been fairly widely adopted. It's present in not just sort of an emerging cadre of products coming out of companies like Johnson Controls and IBM, but also smart building startups. It's being used to enable research at a collection of national labs and international research agencies in Canada, Hong Kong, Singapore, and Denmark. So, and I'm also involved in getting Brick incorporated into parts of a possible international standard through the ASHRAE organization. So this has been coming up. Brick has been doing pretty well. Okay, so now we understand what that graph looks like. How do we create it? If Brick is so great, how do you actually get there? And so the realization here was that there are plenty of existing representations of buildings and things like buildings that support different use cases. You have your architectural diagrams, you have the specification of the controls that are inside the building, you've got the representation of the information you need for energy audits. And while these don't actually support the applications we need, they still contain useful metadata about how that building is put together, how that building operates. And so to make Brick adoption practical, we had to bootstrap the creation of these Brick models from these existing sources that people already had. We need to be able to maintain that Brick model even as that building is changing, even though those representations are changing underneath our feet. And the goal here is not to make brick some universal representation of all knowledge about buildings, but to preserve those investments while enabling new kinds of applications, new kinds of uses of data. And so the challenges here are not just that bootstrapping and the change over time, but also the fact that those representations can disagree. They can have different ideas of what's in the building. They might be constructed at different points of time, and so there's a need to reconcile those differences. And that's the system that that I developed. So to sort of build up this system here, we start with these representations, these digital representations of the buildings, and we take a leaf from the book from extract, transform, load, pipelines, and data integration. And we have this idea of a wrapper. And what that wrapper is going to do is some process that's going to take some representation of the building and turn that into brick. And it might do that through direct translation or transformation of that original form. It might require human input, active learning, or natural language processing techniques. But more or less, we could take something like a haystack model, which is some existing form of metadata about buildings. And through the translation, we actually get some brick metadata out of that. And so each of these wrappers for each of those sources are going to be producing some sort of brick metadata. And now we need to merge that together into one representation that can be used by applications. So the way that this works, there's a reconciliation algorithm that I designed. I'll sort of give you the high order bits here. So you start with all that metadata that has been inferred about from each of those original sources. The algorithm uses record linkage techniques to try and cluster by what it believes to be the same entity, just represented in different sources. And the way it's going to do that is not just through sort of classic string similarity techniques, but also using a novel type or ontology-based alignment technique that I developed. After it creates those clusters, what it believes are the same things, it unions all the statements about the stuff that's supposed to be the same, and it examines that using the formal axioms that are written down in the brick ontology. And if that validation passes, if the statements all seem valid and they all seem correct and nothing conflicts, then we've more or less won. We get that graph. But if that doesn't work, if we say, well, entity X, according to one source says it's a room, and that according to another source, it says it's a sensor, it can't be both at the same time, so something must have gone wrong. The system will then recurse and try to reorganize, recluster, revalidate all over again. And so does this work? Yes. We took two sites with different numbers of metadata sources. We ran it through this process, and we found that more or less the algorithm worked as expected with a minimal number of manual interventions, and with each of the sources contributing, some unique percentage of the resulting model. Okay, so now we know what the building should look like. We know how to get there. Now, how do we actually use that representation to build applications? So returning to this example brick model from before, you can see I've now augmented this picture with the pointers to the actual data. So those points, the data sources, they have a brick type, but they also can now have where is this data actually stored, and how do I get that? And what this is going to do is here's sort of the architecture of how that information will be used. We'll start with an application manifest, which is the description of what's the data that this application needs in order to behave. It's going to query, actually evaluate that manifest against the metadata model or the brick model for a particular building. It's going to use that information to configure its own operation, and then the application logic can actually go and execute and pull the data in as it needs it in order to operate. So sort of walk through how that works. We'll start with the application manifest. This is one or more queries against the graph. And what these queries are going to do is encode both the type and the context of the data that's needed. So the sort of specific details here of what these queries are asking, you can ask about after the talk if you need, but essentially these are two queries. The first one is going to ask for, give me all the data that might indicate that the cooling process is broken in a piece of equipment. So it's asking for the position sensor that tells us if the cooling is on, and it asks for two temperature sensors that come before and after that. So the temperature doesn't change and the cooling is on, then the cooling might be broken. And And what the second query does is give more of the context for those results. So if that were broken, which rooms might be affected by broken cooling? And so the role of these queries is to try as much as possible to account for the differences between buildings and the heterogeneity in that structure. And I'll make that more concrete on this slide. So we've got 3 buildings, 3 basic brick models that represent data sources. And I'm going to concentrate just on that piece for finding the rooms that are downstream of our broken piece of equipment. And you can see that, we have the common elements. We've got the AHU on one end, we've got the rooms on the other end, and there's some stuff in between. And the goal is to write a query that can be somewhat agnostic to the stuff in between, because the relationship between the equipment and the room is going to be captured by brick feeds. And so the way that this query operates is it uses a transitive closure. So you can think of this as sort of traversing as many of those hops that all have the same label as possible in order to find the things that have the room label. And if you evaluate that query across these buildings using the small number of brick relationships, the intuitive classes that brick defines, you can find that you get the correct information regardless of for the most part, regardless of how the structure of that graph in between works. And obviously, the more complex your case gets, the more complex these queries get. But for the basic example, I think this serves. So how does this get incorporated into the workflow? How does that application work? So you express the data requirements, those get evaluated against that brick model. You get back a table of results, essentially the bindings to each of the variables in your query. And some of those, the ones that are points, the ones that have a type that is a point, you can then join against the actual time series data, get your data frame or your matrix, and then you're off to the races to go and do whatever analytics you want. And so I've realized this system in the context of Mortar. Mortar is a data platform that enables self-adapting applications. It also contains over 100 buildings worth of public data that's available for open research. And so each of those buildings has a brick model that describes the data that's there, how that's put together, what that data means, and it provides an API for accessing those buildings, accessing that data in terms of the brick model. And to give you sort of a little peek under the covers of how those applications are actually operating, there's this sort of multi-staged approach. The manifest gets executed early on. It discovers which of those buildings in the data set are appropriate or actually sort of return results for those queries. There's a modular approach to fetching the data, cleaning that up, perform the actual analysis, and then analysis and aggregation of the output of the application is where the application logic actually belongs, or where that goes. And so we went and implemented this. It's not just me, it was a collection of people. We implemented, I think this is 11 applications over a collection of these buildings. And what I want to draw your attention to is that last column there, the percent coverage. And this is when we wrote that application once without changing a single line of code, what percent of those buildings in that test bed were able to successfully execute that application. And most of these are doing pretty well. Upwards, most of these are upwards of 15% of those buildings, which is pretty good given that the standard case is it runs on 1 or less than 1% of the buildings in the test bed. And what we found is the portability of the ability of these applications to run on more than one building was limited more by what data was available about the building. So most of these buildings, if you look at that lighting down on the third from last row, most buildings didn't have any data about lighting whatsoever. And so that's why that's 2%. Whereas data that was more commonly available made it possible for these applications to run on more buildings. And so the ecosystem around this platform has been growing. There's not only an open source library of these applications and analytics that you can actually go and run yourself, but we had broken valve detection app written by a postdoc at Berkeley, Carlos, had reinforcement learning algorithm implemented by another postdoc. I wrote a stuck number fault detection. So these things are real. They run on real data. They give real results. I also wrote an interactive online tutorial to teach people about how that programming model worked. And there's also an interactive query builder that makes it so you don't actually have to know that Sparkle language in order to query these models. You can sort of click around and find stuff and then get that query that you can just paste into your application and that'll run. Okay, so now we've got a bigger picture of that full stack, and I want to do one last sort of dive into a piece of technology that I had to build in order to make this stuff actually efficient and operational. And that's the Sparkle query processing. So Sparkle query processors have been around for some time. They're designed to run on really, really large graphs like Wikipedia large, and there's plenty of off-the-shelf ones that you can use. But despite the fact that these, are supposed to scale up so well, they actually don't scale down. And so we found they actually performed pretty poorly on the kinds of brick models that we were throwing at them, despite those being a fraction of the size. And so our goal was to try and hit 100 milliseconds, sort of classic interactivity threshold, because you want to be able to run these queries in notebooks and an interactive data analytics process. You don't want to have to submit a query and wait for minutes or even hours for a query to execute. And so there's a bit going on here. These are the benchmarks that I ran. Each of these spider graphs is one sort of off-the-shelf database. Some are open source, some are commercial products. Each of the radial axes is one of the queries that I ran. And the extent of that radial axis is how long that took in sort of a logarithmic timescale. And so visually, you can just see that bold septagon near the middle is the 100 millisecond threshold. And most of these queries you can see are executing, exponentially outside of that septagon. So we want to get stuff inside the septagon, but first have to ask, why is this stuff so slow? And it comes down to joins. So we're getting a little bit into the database world, but when it comes to joins, evaluating joins in Sparkle queries, there's two sort of pathological characteristics of brick models that pose issues. The first one is there's just a few number of property names. Remember, it's feeds has point, has location, stuff like that. There's a small number of those, which means that the indices that are being built by these databases actually don't have really good selectivity, which can cause issues. The other one is the heavy use of transitive closure. Oftentimes in Brick, we want to be able to traverse as many hops as we can in order to find relevant information at the other end of a chain. And the processing of these transitive closures is going to dominate query execution. And I'll show you why. So on the left here is sort of a high-level illustration of the kinds of indices that you get in these Sparkle query processors, essentially for each of the triples that constitutes the graph. They create a new index with each sort of combination of those. And so when we're trying to do a transitive closure, we're looking at this predicate prefix index, the things that start with the relationships. And if we're trying to traverse these hops, every time there's a new hop, we essentially have to go back to the start of the index and find that next hop. There's absolutely no way to leverage the spatial locality of these different links inside these index structures. And this poses a significant problem. So what I did to get around this was develop a new kind of index that was more appropriate for the Brick workload. And so I implemented this index in a corresponding query processor in Brick called HOD. And what HOD did was use this neighborhood index that essentially embedded a pre-computed transitive closure inside the graph, and then was able to execute existing Sparkle queries over this new kind of index structure. And so this is a classic trading space and pre-computation for query speed sort of trade-off that works for the kinds of small graphs in Brick. Even if you're replicating all this information, having these big transitive closures, Brick models are small enough that it's actually not that bad. And fundamentally what this does is it transforms the query execution time from being linear in the size of the transitive closure to being linear in the number of query clauses, which is much, much faster. As you can see from my septagon graph, where running those queries on a collection of a couple of buildings, easily falls within that threshold. So that was a success there. Okay, so now you've seen all that work. How does it actually get applied? I'm keeping an eye on time. Got 13 minutes till 4. I can do this. So One of the things I had the opportunity to do with a number of people on this call was deploy Brick and a distributed operating system that we called XBOS in the real world. And what this system did is it interfaced with IoT devices and building management systems and electric vehicle chargers and photovoltaic systems, all sorts of different kinds of equipment. Described them all using Brick. And then we were able to run a number of really cool projects over this deployment that it was in 20 buildings, not just office buildings or residential, but movie theaters. There was a casino up in Northern California that ran this stuff. And so we were running automated demand response, having buildings react to the price of energy in real time, integrating the building control with solar generation, battery storage, and a microgrid, even starting to do new kinds of distributed control frameworks in the smart grid level. So lots of really neat stuff we were able to deploy. This is roughly what the system looked like. We had these drivers that were deployed out in the field, running on little tiny servers or Raspberry Pis. They were able to access the brick model and time series data that was stored up in the cloud or on some other server deployed somewhere in the world. And we wrote visualization dashboards, model predictive controllers, worked with the price of energy, all sorts of things that were connected over this secure message bus written by a prior student and a previous colleague, Michael Anderson. And this was the content of his thesis. So we brought those two worlds together to make that all work. And just to give you a sense of the complexity of some of these tasks. So in order to have the operation of that building react to the price of energy, we had to consume all different types of signals. We had a couple postdocs that were helping to write these models, and we didn't want to have to write those models for all 20 buildings in that deployment. So essentially we wrote that code once. And what that code did is when it was deployed, it went and found the brick model, discovered the data sources it needed, discovered the things it could control, and essentially adapted itself to each one of those 20 buildings. So write once, run everywhere. Definitely sort of the future of where I think this sort of stuff should go. So that's getting to the end of the work that I did. I want to touch a little bit on future work. So one of the things I think this is building up towards is essentially a unified semantic representation of all cyber-physical resources. So being able to look at the impact of design decisions, the impact of retrofits and remodels across different sectors of the built environment. Imagine if PG&E knew what was on the other side of the lines that they're turning off during fire safety, or imagine if a city manager could actually contextualize the air quality readings they're getting out in terms of the infrastructure and services and demographics of the areas that are being affected. And there's been some progress already. I've been working with Sasha von Meyer on the call, some others at UC Berkeley and LBNL on, working on better representations of smart grids. I'm starting to work with the National Alliance for Water Innovation on being able to do the same thing for wastewater treatment facilities and similar processes. So things are getting off the ground there. A fundamental issue here is how does that stuff actually get shared? How does that metadata get shared? There's not one owner of everything. And so there needs to be the need for new primitives to be developed that allow metadata, these descriptions of systems, to be shared across administrative boundaries. Maybe transitively delegating views on those models so that you can give PG&E the ability to see maybe major loads or the meter that's in your house. And getting at the idea that we might be able to have access to that data, access about the physical world, be some sort of municipal service that people could tap into and have privacy aware, semantically rich descriptions of the data in the built environment that allows them to better understand what's going on. There's also a need for new programming paradigms and systems that support this. The stuff that processes the Sparkle queries and stores those RDF graphs, they need to be able to be managed in a distributed manner. We need to be able to run these on small embedded devices. We can't just rely on large in-memory clusters inside the cloud. And so there's a need for doing some development there, new kinds of database architectures, abstractions for working both with metadata and data at the same time, working with different versions of that metadata over time, different semantics over time. There's techniques to be developed there. and also just better programming of all of this stuff. One of the things I've been working on the side, I'm supposed to be writing my thesis, is there a sort of data frame like programming model that could allow these Sparkle queries to be built up with code using a much more intuitive interface rather than relying on this, you having to write these queries out and then execute them in sort of a batch processing style. So in conclusion, I've showed how a semantic metadata model can describe heterogeneous cyber-physical systems. I've introduced a new paradigm of self-adapting software that makes it easier to deploy these things at scale, makes it easier to run these kinds of applications. I've developed new databases and tools that make it practical and efficient to manage and work with these kinds of metadata and data. And lastly, I've proved this out in the real world by deploying these systems, releasing public data sets that foster research and community. And so 2 things before I finish talking. Everything I talked about is open source. It is free. It is available. You can go today. You can look at this. You can read it all. You can contribute to it, use it, whatever you want to do. And that's it. Thank you so much to my dissertation committee for their time and their patience, especially to my advisor, David Culler, who's shepherded me through 8 years of trying to figure out just what the hell I'm doing. And thank you so much to collaborators, colleagues, and friends, especially Andrew Krikov, who took a chance on an undergraduate 8 years ago, 9 years ago, and basically, introduced me to this whole world, which I'm going to continue on. Yeah, just thank you so much. Thank you to Sonia, who's helped me through all of this. Thanks to parents, just thanks to everybody. Great to have you all.
Wahoo!
That's it.
Wow, a lot of stuff, man.